Kindly check your details, sir. I'm going to flash your banner.
Yes, sir.
Okay. So, once again, good morning, everyone. This is a pleasant fifth day of our online faculty development program. We've been conducting sessions on the green energy in the topic of green energy and sustainable development. We have a very apt person for today's morning session. Dr. S. Jesus Thomas, welcome, sir. He is the head of the department, as I already introduced, and he has 28 years of teaching experience, out of which he has accomplished many leadership positions. Apart from that, he has also got 4 years of industrial experience in the mechanical engineering field itself. His expertise is not only in the core of manufacturing engineering, in which he has done his studies, but also into production technology and all other fields. He has contributed to the curriculum development and all other activities in his academic leadership throughout this year. So to give a very significant note about his contributions, the institutional development for his over 15 years of his development of the institution KCG, College of Engineering, his contribution to research and his commitment to quality enhancement are very much known among the faculty members and all over the place in Chennai. His educational background is basically from mechanical engineering and then manufacturing engineering in the post-graduation. And he has completed his PhD from ACTEC campus of Anna University. He started his career as a lecturer in Meenakshi Krishnan Polytechnic College and later joined as head of the department in Sri Durga Devi Polytechnic College, where our colleague here in Weldtech Multitech, Dr. Chandralingam, got accredited to him. There he worked for 5 years, and afterwards he joined B Institute of Technology. And with a stint of 3 years, he has made the past 12 years of his service in KCG College of Technology and holds a leadership position and accomplishments drawn from his guidance. During his industrial experience, he has taken the positions of production in charge in Hawk engines, and he has handled a number of production-related activities and has a good balance of industry as well as the academic, which he is reflecting into his leadership till date. Coming to his research publications, he has more than 10 quality publications, out of which are 6 very reputed journals, and he holds 2 patents in the intellectual property rights category to his credit. Also, his interests are towards the advanced manufacturing technologies and industrial engineering applications. He has already served as a number of times in this kind of forum as a resource person or in the capacity of this lecturer, and he has delivered in various faculty development programs also. In his leadership in KCG and other institutions, he has conducted many guest lectures, seminars, faculty development program, workshops, and the value-added programs, which has benefited to the student community of mechanical engineering. And he is actively involved in the curriculum development, and he has done academic audits and quality assurance, which is another expertise. Not to say much about his administrative power, many people know his capacity to control people as well as work from the community of faculty members as well as the non-teaching faculty. And we have successfully taken many times KCG Institute towards accreditation and passed with flying colors. Actively, he guided students in the undergraduate level, and he is promoting many students to the capacity of mentor. So this is my opportunity to say once again warm welcome to Dr. Jesus Thomas, sir. And To give you a hint, Mr. Sankalingam is to my next sir. He only suggested your name and they have the opportunity to meet you, sir.
Thank you, Professor, for your introduction. Shall I start the session, sir? Am I audible to everyone? Am I audible?
Audible, sir. You are audible. You are audible. You are
Okay,
audible.
let me share my screen. My screen is visible, sir?
Yes, sir. Visible.
Good morning to the respected organizers, distinguished speakers of this FDP, faculty participants, and dear colleagues. It is indeed a privilege for me to be part of this faculty development program on green energy technologies for sustainable development. And I sincerely thank the organizers for giving me this opportunity to serve as the resource person on this fifth day FDP. Over the past 4 days, you would have explored various dimensions of renewable energy, sustainable systems, and emerging green solutions. Today, we move one step further from sustainability to net zero carbon emissions, which is not just a technological goal but a global responsibility. Climate change is no longer a theoretical discussion. Actually, it is a measurable reality. Climate change is a measurable reality. So, rising temperatures, then the extreme weather events, melting glaciers, energy crisis, all this are forcing their nations, industries, and academic institutions to rethink the development models. So the question today here is not about whether we should adopt green technologies. The question is not that. The question is how fast can we transit to achieve net zero. That is the question of today's scenario. So my session today is titled Green Energy Technologies for Net Zero Carbon Emissions. In this session, we'll understand what exactly net zero means, why it is critical for sustainable development, what technologies are enabling this transition, the role of engineers, researchers, and educators in achieving this target. Then, to begin with, let me give the overview of my presentation. Introduction about climate change and net zero, global and India energy carbon scenario, renewable energy technologies, energy storage technologies, green hydrogen and hybrid energy systems, green fuels and life cycle sustainability, green technologies beyond energy, and I have taken 3 case studies and few numerical examples towards the title India Net Zero 2070 Roadmap, and then challenges in achieving net zero, conclusion followed by Q&A session. So, what is carbon emission? Emission of carbon dioxide and other greenhouse gases, we say that carbon emission. Primarily, these emissions are from fossil fuel combustion, industrial processes, and through transportation, power generation, and through construction, all these gases are emitted. So, what is this greenhouse gas? We shortly call it as GHG. It is a gas present in the Earth's atmosphere, which has the ability to trap heat and prevent it from escaping into space. This effect we call it as greenhouse effect, which everybody is familiar. Everybody might be familiar. This gases acts like a glass of a greenhouse, which allows sunlight to enter but trap part of the heat inside, keeping the earth warm. So the process involved in this is the sunlight which has a short wave radiation will enter the Earth's atmosphere. The Earth will absorb some energy and warms up. The energy radiates heat back as infrared radiation. Then greenhouses gases will absorb and radiate some of this heat. This will keep the planet warm enough to support life. So without this greenhouse gases, the Earth's average temperature it would be about minus 80 degrees Celsius instead of the current which we have minus 15 degrees Celsius. So this greenhouse gases are necessary, but it should be limited. The excess amount of greenhouse gases will cause the global warming. The greenhouse gases involves carbon dioxide, methane, nitrous oxide, water vapor, fluorinated gases. All this are from the major sources which we have discussed, like fossil fuels, deforestation, cement industry, agriculture, then fertilizer industry. All this are the major sources of these greenhouse gases. Now, increased greenhouse gases concentration that will lead to more amount of heat getting trapped, and in turn will lead to global warming, and further it will lead to the climate change, which everybody in every country we are experiencing this climate change. Net zero carbon emissions primarily refers to the reducing and balancing greenhouse gases, especially carbon dioxide, in order to stabilize the global temperature rise. Net zero carbon emission as an introductory part in this slide. So the left side of the slide showing the greenhouse effect, where the as I explained the process, sunlight entering into the Earth atmosphere, it will absorb some energy. It will absorb some energy and gets warm up. So energy after then again it will radiate heat back as infrared radiation, and this gases will absorb and re-radiate some of this heat, making the planet warm and supporting the life. So what is this net zero means? It is not zero emission. So many of them will think that net zero means zero emission. No, it is not zero emission. It is something we can say as a mathematical formula, like total greenhouse gases emitted should be equal to total greenhouse gases removed from the atmosphere. If it is the case, then we can say that there is zero emission or net zero emission. So emissions produced minus emission removed should be zero. So we cannot avoid producing emission, but at the same time, the produced emissions, everything need to be removed so as to attain the net zero emission. So normally we come across a few terminologies related to this, like carbon neutral, net zero, zero carbon. So, but there is a slight difference in the meaning. If you say carbon neutral, it is offsetting emissions through credits. If you say net zero, then deep emission reduction plus minimal offset, that means net zero. Then zero carbon means no fossil based emission, because fossil fuels they are the major source for this emissions. So when I say zero carbon, it means that no fossil based emissions. Nowadays, everywhere we are talking about the SDG, Sustainable Development Goals, but in particular SDG 7, affordable and clean energy, SDG 9, industry, innovation and infrastructure, SDG 11, sustainable cities, SDG 13, climate action. All these are very much related to this topic. So net zero is not separate from sustainable development. It is the technological pathway to achieve it. So there are many pillars of the green energy technology, like renewable energy systems, which cover solar, photovoltaic cell, then concentrated solar power, wind energy, biomass, and then small hydropower stations. All these are are categorized as renewable energy system, which is one of the pillar of green energy technologies. Then energy efficient technologies. So high efficiency motor, waste heat recovery, smart grids, LED and intelligent system are part of the energy efficient technologies. Then energy storage technologies, lithium ion batteries, hydrogen storage, then thermal storage, grid scale storage, all this are part of the energy storage technologies. Then carbon capture, utilization and storage, which we call it as CCUS. Then green mobility, the electric vehicles, hydrogen fuel cells, biofuels, green manufacturing and industry 4.0, which covers lean energy system, digital twins for energy optimization, then smart monitoring. All this are the said to be the pillars of the green energy technologies. Now, the 20th century was about the industrial growth. Now, the 21st century is about the responsible growth. So that this statement is very important. I repeat, 20th century was about industrial growth, but 21st century is about the responsible growth. So engineers today are not just problem solvers; they are climate solution designers. So engineers are considered to be the climate solution designers. So over the past sessions in the last 4 days, you would have understood about all the renewable technologies. I hope that all those technologies would have been covered. Today we will integrate them into a system perspective, how these technologies collectively contribute to achieving the net zero carbon emissions. So let us move from awareness to action, that is from sustainability to accountability, and from conventional engineering to climate conscious engineering. With this thought, let us begin our discussion on the green technologies for net zero carbon emissions. So this slide, this shows sector-wise contribution to global greenhouse gas emissions. So understanding where these emissions originate is the first step towards the designing effective net zero strategies. As engineers and educators, we must focus on the sectors where intervention will create the maximum impact. So if you see this slide, the maximum emission is from the power sector, which contributes to about a 26%. This is the largest contributor. So this 26% is the highest value among all these sessions. So the electricity generation from coal, that is your thermal power plant, oil and natural gas, and then fossil fuel based grid system, all this comes under this power sector. So decarbonizing electricity through solar, wind, hydro and nuclear is the backbone of this net zero transition. Next comes the industry, where it contributes to about 11% through manufacturing activities, and then steel, manufacturing of cement, chemicals, and heavy engineering processes. So there the emissions are due to fuel combustion, process emissions, especially particularly in case of cement manufacturing, process emissions are more. So industrial electrification and green hydrogen are the major solution for this industry emissions from industry, which is contributing to about 11%. And next comes the transport. If you see transport, it is about 15%. The major of it is through the road vehicles, and even through aviation, shipping, railways, all these modes of transport also. Through these modes of transport also, emissions are growing rapidly because of the urbanization and vehicle ownerships. So nowadays, all these vehicles which are using fossil fuels are slowly replaced by electric vehicles, which everybody would have noticed. So the solution to this pollution or emission from the transport is the electric vehicles and the usage of biofuels, hydrogen fuel cells, and even the public transport electrification. All these are the solution for this emissions through transport. Then emission from the building, which is about 6%. So residential and commercial buildings, heating, cooling, lighting, air conditioning systems, all this are the sources of emissions through buildings. So energy efficient buildings nowadays, energy efficient buildings, all the civil engineers and architects, they concentrate on preparing the energy efficient buildings and green building design. So all this will significantly reduce this share of about or contribution of about 6%. Next, fuel production. the fuel production, which is about 10 percentage. So we know that fossil fuel from the crude oil, we are extracting all the other petrol, diesel, wax, everything. So extraction and refining of fossil fuels, methane leakage during oil and gas production, and then coal mining emissions, all these are the sources for which contribute to about 10% of the total emissions. So methane leakage control is critical in this sector. Then coming to the industrial process, which contribute to about 9 percentage, in particular cement production, where chemical reaction is happening, which releases carbon dioxide. Then chemicals manufacturing and the refrigerants, the fluoride gases which we use, all this contribute to 9 percentage of the total emissions. So these are not only energy related emissions, but they are due to chemical process emissions. Then coming to the agriculture, there also we have it contributes to about 11 percentage methane from livestock, then nitrous oxide from fertilizers which use in the agriculture land, rice cultivation. So all these are contributing significantly to non-carbon dioxide greenhouse gases. And then land usage and forestry. So this is another sector which contributes to about 7 percentage. So deforestation, land conversion, forest degradation, all this forest which act as carbon sinks were destroyed nowadays for the residential building and flats. Everybody is selling the forest area, everything is sold, and this deforestation is a main source of emission also. So landfills, methane, wastewater treatment, solid waste mismanagement, that also contribute to about 4 percentage. So waste to energy and circular economy principles will be the solution for this emissions. So here, the important observation in this slide is to note that power sector contributes to about 26 percentage, and industry contributes is 11 percentage, transport 15. So all put together, if you see, more than 50 percentage of emissions come from these energy related activities. So this shows that the energy transition is central to achieving net zero. So net zero cannot be achieved by focusing on one sector alone. So it requires a system approach which involving energy transition, industrial transformation, sustainable agriculture, the green mobility, carbon sink enhancement. So now researchers are going on this area. So this is need of the hour also. So now we understood that where the emission come from. Now the next question, logical question is, what these green technologies can address each of this sector. So now we'll explore the technological pathways to net zero carbon emissions. So the chart is not just a data; it is also a roadmap. Each percentage represents an opportunity for innovation. Now, the next slide. So this slide highlights the fundamental connection between climate change and the need for achieving net zero emissions. So climate change is primarily driven by the increasing greenhouse gas emissions from human activities such as burning of fossil fuels for electricity, transportation, and for industrial processes. So as a result, what happens? The global average temperature is rising. So we are witnessing extreme weather events, sea level rise, glacier melting, and ecological imbalances happening across the globe. All this every day we are watching through the TV channels and the newspapers also. Now, the figure which is on the right side, that shows the major sources of the greenhouse gas emissions, where transportation and then commercial and the residential energy use, industry activities, and agriculture, all those are significant contributors. So this clearly indicates that emissions are spread across multiple sectors, not only from just one area. So it is through multiple sources we are getting the emissions. So net zero does not mean zero emissions. It means balancing the amount of carbon emitted with the carbon amount removed from the atmosphere, either through natural sinks like forests or technological solutions such as carbon capture. So achieving this net zero is essential to limit the global body warming to 1.5 degrees Celsius, and this will avoid severe climate impacts. So therefore, we need a deep decarbonization of energy, transport, industry, and buildings. All these are necessary to move towards a low carbon economy. So, having understood the urgency and emission sources, now we'll explore the green technology that will be able to or enable this transition towards the net zero. So, global and Indian energy carbon scenario. So, here this slide presents the current global energy mix and its carbon implications, which is central to understand why the net zero transition is necessary. So, globally, the energy system is still heavily dependent on fossil fuels. Nearly three-fourths of greenhouse gas emissions are linked directly to energy production and consumption. So, if you see this pie chart, oil contributes about 38% of global energy consumption, which is mainly in the transport. Coal contributes to about 24%, largely for the electricity generation and heavy industries. And natural gas contributes about 23%, which is used in power plants and industrial heating. So renewables account for only about 9%. Nuclear energy that contributes to about 6%. So this pie chart clearly shows that fossil fuels still dominate the global energy structure. So in this context, coal remains the primary source for power generation, and oil is dominant in the transport sector. Renewable energy is growing rapidly, especially solar energy, wind energy, but still it need to be more significant in scaling. So the challenge of net zero is not only technological; it is a systemic energy transition challenge. So to achieve this net zero, what we have to do, we must reduce fossil fuel dependency, renewable penetration, then improve the energy efficiency, and electrify all the transport as well as the industry. So, if all the researchers are now focused towards these areas to achieve the net zero. So now I think we understand the dominance of these fossil fuels in the global energy mix. Now let us see how green technologies can help us to shift towards a low carbon energy future. So this slide focus specifically on our country's electricity mix and its transition pathway towards net zero. On the left side, we can observe the evolution of India's electricity generation mix. In 2010, fossil fuels contributed about 84%, and the remaining 16% is through the renewables. And in 2020, renewable share increased to approximately 23% from 16%, and the remaining is through the fossil fuel, 77%. Now it is expected that by 2030, since more focus is on the net zero emission, so there will be a 50 percentage of energy through renewable, and the remaining 50 percentage will be from the fossil fuels. So this target will reflect India's strong policy commitment towards clean energy transition. So this shows that how India is moving steadily from a fossil dominated system towards a more balanced and sustainable energy mix. Now, looking at the current installed capacity breakdown on the right, this is the current installed capacity breakdown. So here, coal again still contributes to the largest share, about around 51%, which explains why India is one of the top carbon dioxide emitters globally. Renewables, hydrogen, use of hydrogen, natural gas, and nuclear together form the remaining share. So while coal still dominates, the growth rate of renewable energy, especially solar energy and wind energy, so that is one of the fastest in the world as of now. India has announced ambitious targets: 500 GW gigawatts non-fossil fuel capacity by 2030. So net zero emission by 2070. So this is our roadmap for our country. So this clearly demonstrates that India is not only acknowledging the climate challenge, but also actively planning a structured transition. So it is not just an environmental necessity; it is an economic and technological transformation opportunity which everybody need to concentrate and put into action. And the next slide, this is about the renewable energy technologies, which almost everybody is aware. So the major renewable energy technologies that are driving the global transition towards the net zero carbon emissions include the solar energy, then wind energy, hydropower, biomass energy, geothermal energy, so where we'll be extracting heat from beneath the earth's surface, from the hot volcanic zone, we will be extracting the heat. All these technologies are crucial because they produce low or near to zero carbon emissions during the operation, unlike fossil fuel based power plants. The most important role of renewables is in decarbonizing the power sector, which we discussed earlier, contributes to the highest share of the greenhouse gas emissions. So renewable energy sources, this wind energy, solar energy, they are intermittent, they are not continuous. So they depend on weather conditions. Therefore, we need to go for energy storage system like the batteries and hydrogen storage. Smart grids and digital monitoring system are also essential to improve the reliability and also to ensure stable power supply. So renewable energy is not just an alternative source; it is the foundation of net zero emission. So we understand that the major renewable technologies can be integrated efficiently to achieve large scale decarbonization. So by going for a hybrid system, using renewable in addition to the production of hydrogen, all this can be used as a hybrid system to achieve the large scale decarbonization. The next slide, the energy storage technologies. So this slide highlights the critical role of energy storage in achieving a reliable and sustainable energy system. So as discussed, the solar energy, wind energy, all these are intermittent. That means it is not continuous. So generate power only when sunlight or wind is available. So electricity demand is continuous and variable throughout the day. So energy storage systems are essential to balance supply and demand. So here the major energy storage technologies include the battery storage system. We use lithium ion batteries that is widely used in grid scale storage as well as in electric vehicles also. Then pumped hydro storage, which is used to pump water to a higher elevation during excess power generation and released to generate electricity during peak demand. Then thermal energy storage, which will store heat energy for later use, commonly used in concentrated solar power systems. Then hydrogen storage system, where excess renewable electricity is used to produce green hydrogen, which can be stored and which can be later converted back into the required energy, specifically electrical energy. So this energy storage will provide several benefits, like it will improve grid stability, enables peak load management, reduces dependency on the fossil fuel based backup power plants. It will support the large scale integration of renewables. Without energy storage, renewable energy cannot fully replace fossil fuels. So to replace fossil fuels, to move on to the net zero emission, we need to go for renewable energy. And in addition to that, energy storage is also very essential. So the storage is the bridge between the renewable generation as well as the net zero target. So having understood the generation and storage, now we'll explore how these technologies collectively contribute to achieving net zero carbon emissions. So here there is a classification of energy storage technologies. So it provides this slide provides a comprehensive classification of energy storage technologies, which is in the form of mechanical, electrochemical, thermal, electrical, and hydrogen based storage. So this classification is very important because different applications require different energy solution. If you take mechanical energy storage, it is stored in the mechanical form. The examples are, we can say, pumped hydro energy storage, which stores energy by pumping water to higher elevation. Then gravity storage technologies, lifting heavy masses to store potential energy. Then by using compressed air energy storage, we can compress air and it can be stored underground. Then we can use flywheels as we use in the engine, where we can store energy in rotating masses. So all these systems are available for low scale grid applications and long duration storage. Then coming to the electrochemical storage. Electrochemical storage, the batteries. So energy is stored through chemical reactions, which includes lead acid batteries, lithium ion batteries, then flow batteries like zinc, bromine, vanadium. High temperature batteries are there. Then zinc based batteries are there, which are widely used in electric vehicles, rooftop solar system, then grid scale storage. So lithium ion currently dominates due to high current, high energy density as well as due to high efficiency. Then coming to the thermal energy storage. So here the stored energy will be in the form of heat, which include sensible heat storage, latent heat storage, thermochemical storage. In case of latent heat storage, we will go for PCM, that is phase change material. All these are important in concentrated solar power plants as well as the industrial waste heat recovery. Then coming to the fourth classification, electrical storage, where energy can be stored directly in electric or magnetic field. Supercapacitors are there, which can be used for fast charging, which takes shorter duration. Superconducting magnetic energy storage, which we call it as SMES. All these are different sources of storing the electrical energy. Then hydrogen-based storage, the fifth one. So energy will be stored in the chemical form as hydrogen. So power to power, which we call it as fuel cell, power to gas. All this are different hydrogen based storage. So for long duration as well as for a seasonal storage and decarbonizing heavy industry, all these are the key technologies. So each storage technology, they play a different role, from short-term grid stabilization to long duration seasonal storage. So a combination of these new technologies or these technologies is essential, very much essential to support high renewable penetration as well as to achieve the net zero carbon emissions. So energy storage is not a simple technology solution, it is a portfolio strategy for energy security as well as for decarbonization. The next, the green hydrogen and hybrid energy systems. So here the green hydrogen is introduced, which is considered one of the most promising solutions for achieving the net zero carbon emissions. So the green hydrogen, how it is produced? It is produced by the electrolysis of water, where electricity will be ideally used from renewable sources like solar or wind, and later by electrolysis the water will be split into hydrogen and oxygen. Now the electricity comes from the renewable. The process produces zero carbon emissions. So hydrogen is not a primary energy source, it is just an energy carrier. So it will store energy and it will release it whenever it is needed in the future. So here the biggest advantage of hydrogen is that it will enable long-term term and short, long term, as well as large scale energy storage of excess renewable power, seasonal energy balancing. All this is possible by integrating this hydrogen along with the existing system. So when these renewable systems are integrated with the hydrogen production, storage, as well as fuel cells, we can create what we call it as hybrid energy systems. So combination of two sources put together. So that we call it as hybrid energy systems. So these systems combine solar or wind with electrolyzers, and then store hydrogen safely, convert hydrogen back into electricity using fuel cell. So here the continuous and reliable power supply is ensured when renewable generation fluctuates. So hydrogen plays a major role in hard to abate sectors such as steel manufacturing, chemical industries, then heavy transportation like the ship, aviation also, they can use hydrogen. But these sectors are very difficult to electrify directly. So hydrogen becomes a clean alternative fuel. So renewable energy is the backbone of the net zero. Green hydrogen is the enabler of deep decarbonization. So hydrogen-based hybrid system not only improve grid stability and energy security, it also provides a pathway to decarbonize sector where direct electrification is not feasible. So the next slide we see the green hydrogen production and the utilization flow. So if you see this diagram, it illustrates a complete value chain of green hydrogen from production to end use application. All these are the different applications which uses the hydrogen. So electricity, we are getting it from the renewable energy sources, either from the wind or the solar. Using that electricity which is stored in the battery, we are using that electricity for the electrolysis process where hydrogen and oxygen are separated, and later hydrogen is used in the hydrogen vehicles and engines where it is converted back to electricity by using the fuel cells. So the entire process, throughout this process, if you take, there is no carbon emission. So this will provide the electricity, which comes from the renewable sources. So green hydrogen connects renewable energy generation with the industry and transportation, making it as a powerful enabler for net zero transition. Then now in this slide, so this is about green hydrogen and hybrid energy system, where the working of a hybrid renewable energy system integrated with the green hydrogen production as well as utilization. Now the electricity is generated from the wind and solar sources, which is converted from AC to DC conversion where required, and it is supplied to an electrolyzer where distilled water is split into hydrogen and oxygen, and this hydrogen can be stored in the hydrogen storage, which can be used for further use, and supplied later. It will be supplied to the fuel cell, which will convert the hydrogen back into electricity when required. This generated electricity, after a DC to AC conversion, it is used to meet the electricity demand, ensuring continuous and reliable power supply even when renewable generation fluctuates. So this case of hybrid systems, even there is a fluctuation. So normally fluctuation will happen only if you use the renewable energy. So in addition to that, if this hydrogen energy system and storage system is used, this will connect the renewable energy storage and then power delivery into a single sustainable energy ecosystem. So this is what we see in this slide. The next slide, the green fuels and the life cycle assessment or sustainability. So we know the green fuels are biomethane, then Fischer-Tropsch fuel, which we call it as man-made fuels produced by converting syngas, that is the combination of carbon monoxide and hydrogen, into liquid fuels like diesel by using a catalyst. So this is what we call it as Fischer-Tropsch fuels. methanol. All these are produced from renewable sources like biomass and biogas. Now, these fuels are obtained by converting biomass using thermochemical methods by the process called gasification, and biochemical method by the process called fermentation, to measure how environmentally friendly these fuels are. We use this life cycle assessment, which we call it as LCA. This will study impacts from the starting stage of resource extraction up to the fuel usage, which we call it as cradle to grave analysis. தொட்டில் முதல் சுடுகாடு வரை அப்படின்னு சொல்லுவாங்க அது. Cradle to grave analysis. So compared to fossil fuels, green fuels can greatly reduce greenhouse gas emissions. But to get accurate sustainability result, we must clearly define system boundaries, and then about the functional units, and we should consider the multiple environmental impact as well as not only the carbon dioxide emission. All this system boundary, functional unit, multiple environmental impact also need to be considered to get the accurate sustainability results. So this slide, process and life cycle assessment of green fuels. So this shows that the process of producing green fuels from the biomass. So biomass feedstock like wood, crop waste, residues, all these are converted into syngas through the gasification process. Then the syngas is cleaned and then sent to a synthesis reactor where to produce the fuel like methanol. So the right side diagram explain the life cycle assessment of biofuels, which evaluates environmental impact from feedstock collection, then processing, then transportation, distribution, and finally as a fuel use. Now the green technologies beyond energy. So in this slide highlights about the green technologies beyond the energy production. So it is not only for energy production, beyond energy production, this green technology can be used, which include a decentralized energy system like microgrid for better reliability, and then carbon capture utilization system, which we call it the CCUS technologies. All this can be used to reduce industrial carbon emissions. It also covers waste to energy and circular economy approaches, which will convert all the waste into useful resource and reduce pollution. So in addition, this green chemistry supports cleaner industrial processes by minimizing the toxic emissions as well as the toxic waste. Finally, the gases, the areas which emerge like ocean energy, sustainable materials, eco-friendly manufacturing, all this will help to improve the long-term environmental sustainability. So this slide shows an integrated green energy system where multiple renewable sources like solar, wind, biomass, and waste to energy, all this will supply electricity, heat, and gas. So this excess electricity can be converted into hydrogen. So from all the renewable sources, the electricity will be generated, and those electricity which is in excess will be converted into hydrogen using an electrolyzer, which we call it as power to gas, and that hydrogen will be stored for the in future use. So carbon capture is also included to reduce carbon dioxide emission and support fuel production. So energy storage system, which we have seen the classification like electrical, hydrogen, and heat storage, all this will help to balance the supply as well as the demand. And finally, the system will deliver electricity and heat to the required loads efficiently. So this is about the green technologies beyond energy. Now we'll take, so I'm here to present 3 case studies where there is a net zero carbon emission. The first case study is the solar battery microgrid for rural electrification. So in this slide, if you see in this case study, it focuses on how a solar photovoltaic that is for PV, solar PV cell, microgrid combined with the battery storage can be used for rural electrification. So in many remote villages, grid power is either not available or it is highly unreliable. So traditionally, these areas depend on diesel generators for electricity, but diesel-based generation has major problems such as high fuel cost, then transportation difficulty, noise, as well as high carbon dioxide emissions. This system, a decentralized solar PV microgrid, is implemented, and that is why the title is Solar Battery Microgrid for Rural Electrification. So, since it uses a decentralized solar PV microgrid, it is named a solar battery microgrid for rural electrification, which means that electricity is generated locally using solar panels instead of depending on a central power station or the national grid. So, to ensure continuous supply, the system is integrated with a battery storage unit. During nighttime or during daytime, the solar panels will supply power and also will charge the batteries. During nighttime, when we are not able to get the energy, solar energy, or during the cloudy condition, these batteries will supply electricity. So the main purpose of this microgrid is to replace the diesel generator and also to provide a clean, reliable, and cost-effective energy solution for rural communities. So the components involved in this system are the solar PV array, which is the main power source. So it will convert sunlight into DC electricity. It generates maximum power during the daytime. And the second component is the battery energy storage system. So it will store extra energy produced during the daytime and provide the electricity during nighttime, cloudy weather, and during the peak demand period, and it will help to improve reliability and ensure uninterrupted supply. And then the third component is the inverter and controller, which uses solar panels and batteries to produce DC power, but household applications require AC power. So inverter will convert DC into AC. So the controller will manage charging and discharging of the battery, power flow control, then protection from overcharging and deep discharge. All this will be managed by the controller. And the fourth component is the local distribution network. That is the network which supplies electricity from the microgrid to nearby homes and loads, including wiring, poles, protection device, and then energy meters. All this will ensure safe delivery of electricity to the village. So overall, this solar battery microgrid will provide clean energy, and this will reduce the dependency on the diesel. It will lower the emission and it will improve the quality of the life in the rural areas. So now in this, if you see the diagram which is provided for the case study, it shows the working of a solar PV battery microgrid. So the PV array will be generating the DC power from the sunlight to the local distribution line, and it will be used to charge the battery banks. Where when solar power is not available, the battery banks will provide the backup power. So finally, electricity is distributed to multiple houses, residential areas, and also to the DC loads like light, fan, and even for mobile charging through the microgrid. Now, this slide shows the performance and impact of the solar battery microgrid system. It significantly reduces the diesel consumption by about 70 to 90%, leading to a major reduction in annual carbon dioxide emission, which is about 1,000 to 1,500 tons at a community level. So this system also provides reliable 24-hour electricity without intermittent supply. Continuous supply can be ensured. So it provides a reliable 24-hour electricity with lower operating cost compared to diesel generators. So overall, it will improve the energy access it will support the local economy and promotes the sustainability. So the key outcome here is the decentralized renewable microgrids, which are used as a scalable solution for low carbon rural electrification and also for better energy resilience. Now I'll move on to the case study 2, renewable hydrogen hybrid energy system. So this case study explains about the renewable hydrogen hybrid energy system, which is designed to provide continuous clean power. So when I say clean power, it is without net zero emission. So since solar and wind energy always they are intermittent, excess electricity is used in an electrolyzer, as we have seen in the previous slide, where it will be split, water will be splitted to produce hydrogen. So the hydrogen will be stored in the tank and later converted back into electricity by using a fuel cell. So whenever renewable power is low, to avoid intermittent power supply, this system can be used. So it mainly uses solar PV or wind turbine and electrolyzer to separate hydrogen and oxygen from the water, and hydrogen storage tank, and then fuel cell for converting the hydrogen to electricity, and a power management system to control all the energy flow effectively. Now this is the diagram for the renewable hydrogen hybrid energy system. This shows the working of a renewable hydrogen hybrid energy system. Electricity is generated from the solar panel and the wind farm. So this sources may not be available continuously. So the generated power will be first converted and managed using AC/DC and DC/AC converters. So excess renewable electricity will be available, which is supplied to the electrolyzer where hydrogen and oxygen are separated. Later, hydrogen will be stored in the hydrogen storage tank for the further use. So whenever renewable power is low or during night time, the stored hydrogen is fed into the fuel cell for conversion into electricity to meet the electric demand. So overall, this system ensures continuous clean energy supply by storing renewable energy in the form of hydrogen. Now, the performance and impact of this system it shows that it will convert excess renewable electricity from solar and wind, which acts as a long-term energy storage option. So, during periods of low solar or wind availability, the stored hydrogen provides backup power through the fuel cell for ensuring the continuous electric supply so it will avoid the intermittent supply. So the system uses renewable energy. So overall life cycle, the carbon emissions is reduced to by 60 to 90, reduced by about 60% to 90% compared to the fossil fuel based systems. So it also provides grid stability and also the renewable penetration. So finally, this hybrid system will support the decarbonization not only in the transport and industrial application, making it as a strong solution for the large scale renewable integration, long duration storage, and also for achieving the net zero energy goals. Now the third case study. So it is one of our student project where so he created a project which implemented near the coal power plant to capture carbon dioxide directly from the flue gas using the microalgae cultivation. So here this case study discusses how microalgae are used to absorb carbon dioxide from the exhaust of the coal power plant. So we know that coal power plant or thermal power plant contribute much to the emission, and those gases, carbon dioxide, will be captured by growing the algae or cultivating microalgae, which will absorb all the carbon dioxide from the exhaust gas or flue gases from the coal power plant. So if this pilot projects are located near the power plants to capture emissions directly and convert them into useful biomass. So here the flue gas contains about 10 to 15% carbon dioxide, which will be bubbled through photo bioreactors or through open ponds. So there are these are special systems that allow microalgae to grow while being exposed to light, nutrients, and carbon dioxide. So photosynthesis will be used to absorb carbon dioxide. So microalgae will use photosynthesis to absorb carbon dioxide from the gas and convert it to biomass, which is an organic material, which can be later processed into biofuels, other useful products. So the when provided with sunlight, nutrients, and water, algae grow rapidly, so resulting in high or efficient carbon dioxide utilization. So if you see the performance metrics on the carbon dioxide capture efficiency, it shows a significant potential for emission reduction. Carbon dioxide fixation rate, it is about 1.5 to 2 kg carbon dioxide per kg algae biomass. And then if you see the growth rate, the algae biomass will double in 24 to 48 hours, indicating very fast growth compared to other biological systems. Then coming to the oxygen release, during photosynthesis, the algae will release oxygen, which will help to improve the quality of the flue gas before it is released to the atmosphere. So this technology demonstrates how biological carbon dioxide capture using microalgae can serve as a sustainable and cost-effective method for mitigating emissions from the fossil fuel-based power plants. It also produces valuable biomass which can be used for thus supporting a circular as well as a green economy. So these are the few data parameters which has been observed with reference the date and time it is given. It is somewhere these algae are cultivated near the location of the power plant, and all these details were collected. So the study includes laboratory testing in Chennai with controlled conditions like temperature, light intensity, as well as then humidity. So the gas measurements, gas carbon dioxide concentration over time, and also a corresponding increase in the oxygen percentage, oxygen generation. So this will result in the it will result in algae health parameters like pH value, turbidity, biomass, and also there are some performance indicators such as carbon dioxide removal rate, which is about 300 ppm per hour, and system efficiency is about 46 percentage. So all this are the details or the experimental results. This is done as a project by our student. Now, the next slide. So this project explains the practical benefits and outcomes of using microalgae based carbon dioxide capture near the coal power plants. So it will highlight that algae biomass produced can be utilized for multiple valuable applications such as biofuel production, biodiesel, bioethanol, biogas, then animal feed, fertilizers, bioplastics, high value chemicals. Along with that, there is an added advantage of supporting the wastewater treatment, which is very beneficial. Also, this will enable the carbon capture and renewable bioresource production simultaneously, which requires lower energy compared to conventional carbon capture methods, and a strong potential to be scaled up for industry like power plants, refineries, cement factory, and also steel sectors. And this slide shows some numerical examples showing how different green energy technologies will help in reducing the carbon dioxide emissions. I have shown a few numerical examples. See, 1 megawatt solar power plant will generate 1.5 million kilowatt hour annually, avoiding nearly 1,350 tons of carbon dioxide per year, which is compared to coal based electricity over a 25 year lifetime, if you take, this will result in a total reduction of about 33,750 tons of the carbon dioxide. So this also compares the EV as well as the petrol car emissions, which indicate that replacing a petrol car with an electric vehicle can save around 1.8 tons of carbon dioxide per year for typical driving distances, say 15,000 kilometers per year. So a 2 megawatt wind turbine can produce about 5 million kilowatt hour per year, leading to a carbon dioxide reduction of approximately 4,500 tons per year. All these are some numerical examples which we can see by going for the net zero emission or going for the green energy technology. Will be able to reduce the carbon dioxide emission to a much extent. And then battery storage peak shaving. So here, so this slide, 1 megawatt hour battery shifting peak load reduces by 15 to 20 percentage in microgrid system. Also, the potential energy or the potential of the hydrogen energy storage, where 1 kg of hydrogen will have 33 kilowatt hour of energy, which is sufficient to supply the basic electricity needs of an average home, which we call it as basic for 1 day. So for carbon capture, it notes that capturing 1 million ton of carbon dioxide per year can reduce emission to about 20 to 25 percentage of emissions from a medium-sized coal power plant. So finally, this renewable energy penetration is limited to 30 to 40 percentage without storage, but with the effective storage system, enabling cleaner and more reliable power grids, will be able to increase this percentage to 70 to 90 percentage, which will provide cleaner and more reliable power grids. So this slide shows how storage and carbon capture improve the feasibility of large-scale renewable energy adoption. And then this is the roadmap for India Net Zero 2070. This highlights the main strategies that are required to reduce the greenhouse gas emission over the period 2020 to 2070. So this is for the period 2020 to 2070. The chart shows that the India's current emission scenario is around 160 GT CO2e, and achieving net zero will require strong action across 7 key levers. So what are they? Renewable energy expansion, and then material circularity, and then recycling, then carbon capture, storage and recovery, natural climate solutions, and sustainable framing, scaling up green hydrogen, electric vehicle penetration. All these are the 7 key levers. So together, these interventions can significantly reduce cumulative emissions with an accelerated pathway, potentially cutting emissions up to 50%, and this require large-scale investment of about $5 trillion. So the India's net zero target depends on a combined effort in clean energy, sustainable practices, as well as advanced low carbon technologies. Now, the net zero scenario pathways for electricity generation sector. If you see this slide, this for the electricity generation sector, this shows how power production must evolve to meet the roadmap which we have seen in the previous slide, India's 2070 net zero target. So the left side figure presents future electricity generation trends under different scenarios, such as low hydrogen adoption, high hydrogen adoption, with the carbon capture, without carbon capture, and storage. All this indicates that electricity demand will continue to grow significantly towards 2100. So which requires a major shift towards the clean energy sources. So the right side graph shows the decline in the coal-based power capacity across net zero scenarios, which reduces sharply. There is a sharp reduction is there after mid-century, especially when renewable energy, hydrogen, and then carbon capture system technologies are adopted. So the net zero in the power sector requires the rapid expansion of the low carbon electricity generation, reduced dependence on coal, and the integration of hydrogen as well as CCS technology for a sustainable energy transition. Then net zero pathways for electricity. Now here this left side diagram shows the share of the solar energy in electricity generation under different net zero scenarios. It indicates the solar contribution increases rapidly after 2030. There is a rapid increase and reaches around 60 to 70 percentage of electricity generation by the second half of the century in net zero pathways compared to much lower growth in the reference case. So the right graph presents the total installed solar generation capacity over time. It highlights the solar capacity must expand massively, reaching several thousand gigawatts by the year 2070 to 2100, especially in scenarios involving hydrogen adoption and carbon capture support. So, achieving net zero will require large scale solar deployment, making solar energy as a dominant source for clean electricity in the future power system. Then this slide shows the projected generation capacity under various net zero 2070 scenarios, focusing on two major low carbon technologies. One is the wind power and another one is the nuclear power over the period from 2020 to 2100. If you take the wind power capacity, it shows a rapid and large scale expansion of wind energy beginning from around 2035 to 2040 under a net zero pathways when capacity increases sharply and reduces approximately 1500 to 1200 gigawatt by 2070 to 2080. So depending on the hydrogen demand and the CCS deployment. So after 2080, capacity stabilizes with slight variations. So in contrast, the reference scenario shows only gradual growth, remaining significantly lower than the net zero pathways. So this highlights that achieving net zero emissions requires a massive scale up of wind energy infrastructure also, not only solar, wind energy infrastructure also. Now coming to the regulatory issues, so regulatory issues show slow policy implementation and then limited financing delay. All this are required for clean energy deployment. The material and supply constraints are also there. We need the dependence on rare earth materials. Then scaling difficulties affect the long sustainability. So, in conclusion, for overcoming technical, economic, infrastructural, and policy changes, we need to ensure sustainable resource availability and grid stability. And this slide shows a multi-level perspective on achieving the net zero. So the landscape level, economic, political, social, and environmental system. All this creates external pressure that will influence the energy transition. So at the bottom, if you see the innovation niches are such as renewable energy projects and pilot programs drive change by generating learning and influencing the policy reform. So the net zero requires a coordinated transformation across policy, technology, markets, and broader socio-economic systems. Now, the green energy for sustainable development, achieving net zero in future. So the major shift from fossil fuels to renewable energy sources is essential to reduce the carbon emissions. So renewable energy along with the storage and production of hydrogen. So all put together, the combined renewable energy with energy storage as well as hydrogen production will form the foundation of the net zero energy system. And carbon capture utilization and storage, capture utilization and storage, which we call the CCS, that will help to reduce emission from the hard to abate sectors, which we call it as heavy industry. So hydrogen production through electrolysis, biomass, storage tanks, underground tanks, then distribution through pipelines, trucks. All these are said to be the key components that are required for the clean energy transition. All this need to be integrated. The smart grids, demand response, environmental monitoring, advanced combustion system, hydrogen engines, fuel cells. All this will support efficient and low carbon energy use. So, to conclude, successful net zero transition requires coordination between technology, then policy, finance, and the stakeholder collaboration. So, sustainable net zero future depends on clean energy adoption, and then hydrogen integration, carbon management technologies, strong policy as well as the institutional support. So, with this, I conclude my presentation. If any queries, please. Hello. Is there any queries? Hello. 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 No queries. Sir, HOD sir. Muthukumar sir. So I completed my presentation. Am I audible? Hello.
Sir?
Sir, I completed my presentation.
Sir, any questions from the audience, sir? Oh, okay, thank you, sir. Thank you, sir.
So thanks to the organizer.
Any other discussion from the audience?
So this is a practical difficulty in the online presentation.
Sir, there is a query maybe left unanswered, sir.
Okay.
Like a role of green banking in the transaction.
Green banking in the transaction. So
transition, sir.
Transition. Yes, definitely. The role of green bank, which covers, as we have seen in the slides, green bank which covers usage of renewable energy put together with energy storage, production of hydrogen. All this put together, we say as green bank, definitely it will lead to the net zero emission. No doubt in that.
Very good, sir. Very good, sir. And some more questions are coming up, sir. Like green technology affect the economy. Obviously, it will boost our national economy.
Definitely, at the initial stage, it seems to be the economy gets affected, but at the latter stage, there are many, actually many advantages only, merits only we have. But it is a need to move towards net zero emission by means of this green energy, green sources. Definitely, it is a need of the hour. There is no other way.
Definitely, sir. Definitely. This question was asked last session, sir. Like, how do we distinguish between carbon neutral and net zero in terms of carbon potential?
Yes, I have shown in that slide. I think the carbon neutral. So, carbon neutral deals with offsetting the emission through credits. Whereas net zero, this is another terminology where deep emission will reduce with a minimal offset. When you say zero carbon, there is no fossil based emission. So until we go for 100% usage with renewable and hydrogen all put together and completely avoiding the fossil fuel, we will not be able to achieve the net zero carbon emission.
Well said, sir. So the world is moving towards a new horizon, like only renewable.
I hope that I answered your question.
Yes, sir. I completely agree with your answer. And why people are asking in many ways the same question. The topic itself is green energy technologies for sustainable development, sir. And before earlier sessions, we dealt with hydrogen-based energy, even wind energy.
Maybe, might be many of my content also would have been covered in the past 4 days.
No, sir, yours is unique actually. Yours is unique.
Okay,
The way of presentation itself is very, very different. The way you give the content is very beautiful, sir. Very beautiful. I think out of the consolidated session in the earlier days, your session stands out in making out complete scenario about this green energy.
Thank you, sir. I think I have not exceeded the time limit.
No, sir, not now.
So till 11:30 you have given time, no? 10 to 11.
Yes, sir. It's a very healthy practice to also debate on something during this session, sir. And people, I think the audience over here will have clarified by having a discussion with you.
Sure.
Also, not only monotonously listening, people have been always posting questions, sir.
Okay.
I will restrict to 1 or 2 questions only. If people ask you in person some of the scenario like this, with your permission, I may give you your email ID so that they can pass on some future opportunities for engaging you in some similar events. Sir.
Definitely, sir.
Yes, sir. It is our pleasure to have you on this session. Like we didn't have a chance, unless Dr. Sangaralingam had given your name. And I know about KCG's image.
Okay. It's an opportunity for me, sir. I should thank the HOD. I think his name is Dr.
Dr. Selvam. Dr. Selvam is the chief coordinator.
Okay.
Myself, I am a co-coordinator.
Okay. Thank you very much. I also thank Dr. Sankaralingam, Professor Muthukumar sir, and all other faculty for giving me this opportunity to present this topic. Thank you very much, sir. Thank you.
Pleasure is ours, sir. Pleasure is ours. We will hope to meet in a forum in person, sir.
Sure, sir.
Yes, sir. Whenever it is possible. Thank you, sir.
Thank you, sir.
Audience, just is leaving, but anyhow, we can stay in the session. Next announcement. Today we will have another session in the afternoon, starting at 1:30. We will join with Professor from VIT Vellore, Dr. A. Satish. He is going to deliver a session on the green energy frontiers, particularly about storage of green energy related to hydrogen. So I hope the afternoon session will be even more engaging. We have 3 sessions slotted in the tomorrow's day, morning 1 and afternoon 2. And tomorrow is being Saturday. Everyone will be mostly free. So make yourself comfortable to listen even when you are traveling. So this is going to be a very engaging session in the afternoon. So we will cut the telecast right now, but afternoon by 1 o'clock we will again join in this session, so that by 1:30, let me confirm with the timing. 1 second. Satish has agreed to deliver the session in the afternoon, and he has been given an afternoon slot only after lunch. So we may possibly join by 1 p.m. If time permits. 12:30 we will start the telecast in another 1 hour. so that everyone will be able to continue the session from 1 p.m. to 2 p.m., 2:30 p.m. If possible. Thank you everyone. If you are staying in the session also, no issues. We will temporarily cut this morning session. Any questions on the feedbacks, you need not bother, sir. There are a number of times you have put feedback related, attendance related things. I should thank really the people who are asking the questions in the forum. Dr. Ramanandan, yesterday query was asked by the external participant. We should thank especially Mr. Bhuvanesh for asking the curiosity questions and clearing the doubts. Okay. So we will meet at 12:30 and the session will begin at 1 p.m.